all, welcome to our second session AICTE ATAL-FDP. Today as resource person we have Dr. Debashis Chatterjee, Professor, Department of Electrical Engineering, Jadavpur University. May I now have the honor to read his biodata first. Dr. Debashis Chatterjee received BE degree from Jadavpur University in 1990. The ME degree from the Indian Institute of Technology, Kharagpur in 1992 and the PhD degree from Jadavpur University in 2005. Dr. Chatterjee has 11 years of work experience in various reputed and renowned industries. He has worked in the National Radio and Electronics Corporation Limited, that is Tata, as Senior Executive Industrial Automation and Electric Drives Design. He has served in Compton Briefs Limited as Senior Executive Industrial Automation. Then he has worked in Philips India Limited as Assistant Manager R&D in Lighting Electronics Design and System Design. After that, he has joined the Jadavpur University as lecturer, and since 2012, he has been working as a professor in the Electrical Engineering Department of Jadavpur University. Dr. Chatterjee has a very profound research experience. He has enriched his academic career with very high quality research publications. Dr. Chatterjee has published 67 papers in numerous peer-reviewed journals like IEEE Transaction, IEEE Access, IET Renewable Power Generation, IET Power Electronics, etc. He has published 46 papers in several national and international conferences and 2 book chapters. His research interests include speed sensor, less control of induction motors, speed sensor, less control of induction generators, microgrid control, efficiency optimization of electric drive system, electric vehicular drive development of solar as well as wind hybrid system, and synchronization to grid. This is all about our Dr. Debashis Chatterjee, Professor, Department of Electrical Engineering, Jadavpur University. Now please, sir, over to you.
For their effort only, we have come here and see many persons from different places and some exchange of thoughts at least. That what I know, what I feel, and what you know, and you can exchange thoughts among yourselves. This has become a platform, right? So that is why I thank these organizers for their to take this pain. They have taken the pain, but beneficiaries are us. So we are able to interact. Okay. And then, and this topic also, I think they have chosen a very wonderful topic as per the present scenario, say power, or what we are going to have a paradigm shift in the next 2 decades or so, from the conventional to non-conventional, or from regular to renewable, you can say. And several techniques are going to arrive so that we are able to extract the benefits of these natural resources what we have, what we call them as renewables. Okay. Now energy, what we see so far. Now this is a topic: grid integration of wind energy is one of the topmost renewable energy sources. Now, if we see here, till now, the source of electrical energy, what we have. Now, the current scenario, maybe this is a 5-6 year old data, but till now, 2-3% here or there, this thing remains same. Right? So, what we find here, that, see, this portion is almost half, 50%. We are getting from coal, right? And then another 20% around from natural gases and all. And rest are all, you can see, petroleum also is a natural product, right? So these 3 is almost say 75%. right? And rest 25%, what we get, this is around 20% for nuclear, or say lesser now, and then hydroelectric and other, maximum it is 8 to 9%, right? So then the scenario is such that we are utilizing mostly the natural resources, I mean fossil fuels, you can say, right? And the catastrophe is, there are 2 points. One is actually, first of all, it's a fixed resource. It is going to drain out over the years, and draining out also. Now I have not presented you other things like that, how it is happening and all, but anyway, it will drain out. Everybody knows. It's not a new thing I am speaking about. And another problem is that it actually releases a lot of toxic gases, including greenhouse gases, to this atmosphere. They are not atmosphere friendly, right? Extracting energy from this. And thirdly, what people mostly do not talk about, say, while conversion, we incur a high amount of, rather you can say, low efficiency. Now, if you see a steam turbine and boiler system, etc., the overall efficiency will never be more than 30%. Now, where this 70% goes? So it is actually coming out as heat or something, right? So you see a lot of heat being released in the nature also. Now, these are the toxic effects of extracting energy from them. Now our aim is to slowly shift this scenario towards this hydroelectric and other. Now other is 3%. It is a 5-6 year old data. It may be 4 to 5% down, around 4% or so. But that is still a poor figure. That is still a poor figure. So globally, there is a, you can say, there is a drive to shift the energy scenario towards this renewable energy, or you can say green energy system, right? Now, if you see here the major renewable energy sources, they are these wind, solar photovoltaic, micro hydro, tidal, geothermal, fuel cell, biomass. I mean, these are the typical things what we have as a resource of electricity. Now, out of which you see the major player are these 3: wind, micro hydro, and solar photovoltaic. Wind, micro hydro, and solar photovoltaic. Others are actually in percentage of total energy consumption, they will not come even 0.5% or so. So the major players are these 3. Now we are trying to look at this in this lecture. Say what are the technologies actually involved to convert this freely available wind energy to electricity, and then what are its difficulties, right? Methods and difficulties, and how we can do, and possible research areas. Now our aim is mainly to find out, to motivate some people to that's why we are moving here and there, to motivate some people to get their research area within this, so into this area, so that some good things come out. So that, till now the technologies are not very sure or not very specific. There are many ways. Each system has its own advantages and major disadvantages. So we can attract people to do research on this. So that is why we are trying. Now the thing is that why we have taken wind, why we have taken wind, that is what I have in my own, this thing arranged properly. After sending, I thought that few pages are here and there flipped, and I have added 2-3 pages, but initially okay. So that is why. Now if you see this page, it will be very clear. Now you just see this line. And how much energy? Actually, whatever the energy we are spending, all has been received from sun. Now the fossil fuel also, it is due to the some animals or some say charcoal, which is also some plant, right? Now here, I mean, if you leave that, the earth, is receiving this much of energy per hour from the sun, 1.74 into 10 power 17. This much of energy it receives. It's a data, it's a known data. Now, see this slide. Now, about 2% of this energy is converted to wind energy. And that is so huge that it is more than 50 to 100 times or around 50 to 100 times more than the energy converted to biomass by all plants on earth. Getting it? So the abundance of wind is the maximum. I mean, among the all renewable sources what we have, the abundance, availability is the most for the wind system. Okay, and it is not new that we are right now going for a move to generate electricity from wind and all. It was known from long back, even before Christ also. The Persians before Christ, they also used wind to do something, like say water pumping or irrigation system or husking, etc. But the problem is that the renewable energy, what we have so far, now we have categorized them into this, the wind, solar, micro, hydro, tidal, geothermal, biomass. So up to this, fuel cell you forget. Now these are all uncontrollable energy, uncontrollable. Means there is no prediction available, right? Or not known that I have this much of wind. And after 5 minutes or even 15 minutes, I can have this. It is very difficult, uncontrollable. Wind speed will be widely varied, okay, throughout the day. Now, controlling that and getting into a usable nature is the major challenge, and that is why we could not do from that period, because we had no knowledge about how to control it. Nowadays, we have equipment, like we have wonderful processors that can compute very fast and with VLSI techniques available, and it is compact. And we have also, programming things that is available, anywhere. Like say, example I am giving you, nowadays even a first year student, even who do not go to engineering also, they can program and run a drone or something. It is very easy for them, because the programming kit, the ICs and the microcontrollers, they are readily available, and the language is also such that you need not have to study that much. But if you think 20 years back, say 2002, 1996, we had to depend on the processors, the digital signal processors of Texas Instruments, having big languages and all. We have to read many things to program it. But now it is very, very easy. And secondly, the power devices. Now, if you see, the power control is only through power electronics. No? That is why the term came power electronics. So the device technology has also been increased very heavily, very significantly, you can say. Now we have devices like IGBTs, even higher bandgap devices like say SiC, silicon carbide, gallium nitride. Those devices are also coming, and they can handle large power and at a very fast switching rate. So all these things have made everything possible so that we can control these uncontrollable sources. Getting me? This history, I'll come back to those pages afterwards. You see this history. Now, what is said, it is being reflected. Now 2200 BC, before Christ, wind-powered machines utilized by Persians. That's what I say. Now see, there is a gap, around 2000 years gap. If you see minus 200, and if you add plus 200, it is 2000, it is 1900 something, right? So then after 2000 years, actually the first development of windmill came in Cleveland, Ohio. This is why, because that time the motors were available, induction motors, some DC generators, those were available, but without any control. Right? Again you see there is a gap of 100 years. 1980s, first modern wind turbines came. Now that also could not be used too much. Now this 1980s, we had the devices like we had thyristors, we had power transistors, we had some processors we have said from Texas Instruments, although it is difficult. But still it is coming. LSI circuits, not VLSI, large scale integration circuits. So 1980s, modern wind turbines. Now after that, we have said past 20, it is past 40 years, it is 2020 now. This lecture is from a little bit back, which I prepared. Now, past 40 years, there are a lot of modernizations, lot of improvements, everything came. So that we are now sitting at a point where we are able to have a good control over it. Not I have said 100%. There are always improvements coming. It is not that we have reached some limit or something, right? So now you see how we do it. As we say, it's an uncontrollable source. Now we call them as distributed energy resources. Now, DER or something you call in power system. I mean, I think some of you are familiar with this term, right? Or distributed generation, DG, right? Distributed generation. Now this basic block, this will be actually your raw source, as I have said, for a wind turbine, wind power, it will be a wind turbine. And then we have a power electronic interface, right? Power electronic interface, this is a key factor. That's what I am telling. This power electronic interface is actually responsible to convert this uncontrollable energy into controllable one, right? Why uncontrollable, again will be discussed slowly. Then to do that, we require several feedback systems like say measurement, feedback and all, and some control and protection system, okay? So this is the basic block diagram. Now in this small lecture, whatever time we get, we will be concentrating on this part. Now what is the power interface? How it is actually converted? What are the techniques, etc. So now come down to this. That's the same thing I have said, that power electronics technology plays an important role. Now this first evolution is due to development of first semiconductor switches and introduction of real-time control. The same thing what I said has been written here. Now you come to this. So this is the actually structure of ancient windmill. That for showing purpose I tried to show. Now let us come to some scenario. Now a few minutes back I told you that wind is the most abundant source of energy, or is the mostly available. Now we will see that in the context of it's a very old data, but still I mean ratio is almost same. Where we stand in terms of wind power generation. So forget rest of the world. Now 1, 2, 3, 4, and we are fifth. Right. Now India is not far behind. That I am telling you. They are among the all developed countries. We have acquired a place around fifth position. in wind power generation. Now in India again, if you see the total renewable energy, see wind is almost 3/4. Now it is data 2015 by MNRE, another data we have, this is about 20 gigawatt. Even it has surpassed solar, right? Now here also, the next year data, wind is this, 61%. So actually see, is the most abundant source and we are trying to utilize also. And in next few years or few decades you can say, there will be a lot of generation of jobs also. Not only that, some research, that whoever will be joining the power sector, they will be definitely coming across this type of renewable sources and their skills to control it, and then they will get some age. So you must study this part very thoroughly. Okay. So this is one. And again, global scenario also you see, this is up to 2020 estimated. PV, this is green one is solar PV and this the black one is wind power. So in global scenario also, it's not in India, I'm just telling. Global scenario also, wind is playing a major role among all the renewable sources what we have. I mean, this is corroborated what we have said in the beginning, that availability is maximum, right? So now come to the technologies. Now technology is grossly, actually wind is a mechanical power, right? Wind is a mechanical power, right? Now that mechanical power has to be converted to electrical power. That means free-flowing wind, say it is in horizontal, so we have to have some mechanism to rotate a generator, right? Through a prime mover. And that prime mover is nothing but wind turbines. So then primarily we have wind turbine as a converter from say linear motion to rotational motion, and that becomes the prime mover for the wind generators, right? And wind generator can be anything, as we have said. It can be a DC generator, it can be AC generator. AC generator can be two types, maybe synchronous, maybe induction, whatever. Okay. So that we'll see that which one to take and which one not to take, what are the factors. Now earlier on, as we say, that DC generator is a problem. DC generator is a problem. Why? Because it has commutator and brushes in the circuit. Right? Commutator and brushes in the circuit. So therefore, regular maintenance is a hindrance. After say each 20 hours, 30 hours journey, you have to of operation, you have to change the brushes and etc. And also you see that it generates DC power and it cannot be operated under say any hostile condition, like say if it is too much of rain or moisture, so there can be short circuiting at the commutator terminals, etc. It's a risky affair. So therefore DC generator is almost ruled out, right? Now AC generator, you see there are two types, as I have said. One is synchronous, another is induction generator. Now synchronous generator, you see that its frequency, generated frequency, depends on speed. Now you know this formula very well, 120 F by P, etc. And then this is the speed of the machine, right? So now if the speed varies, everything remaining same, frequency will vary. Because pole cannot change, right? So this variable frequency operation is a very, problematic affair. As because the generated frequency is different, so we cannot use it to any AC loads, normal AC loads, right? So therefore, earlier technologies had fixed speed technology. That means somehow we have to make the turbine rotate at same speed, whatever with the wind speed, with some gear arrangement, with some say brass tilting and all those things. Sorry, blade tilting and all those things. But it is not a very fruitful thing, as because majority of the power has to be bypassed. We cannot convert the with good efficiency. Suppose my available power is X, So we can convert only 10% of that or 15% of that at peak speed. So now the investment for total thing is lost. I mean recovery time, everything is lost. So therefore this thing came, variable speed technology. And this has not only made it possible to operate at variable speeds at a wide range, but also overall efficiency has increased by around 5%. Overall efficiency. Now here efficiency is a little bit, you can say, not very significant term. There, it's a thermal plant. Efficiency is significant because we are spending the coal energy. And efficiency is less means resting is lost. Now here energy is available freely. Now efficiency low means it has got not much difficulty. It is available, we can convert up to this. That's all. Right? But the thing is that whenever you have a motor, remember, whenever you have a motor with say 80% efficiency and a motor with 90% efficiency, let us say. Now the life expectancy for the 90% efficient motor is more. Why? Because that 20% is lost as heat. Now heat is where temperature will rise, there is more chance to burn the insulations and all those things. So efficiency high here means our system becomes more reliable. Got it? Now you install a system, you don't expect it to fail by next 12 hours. So efficiency high is always important here for the safety or for the, you can say, reliability of the system, not for the losing some energy. Okay. Now easy control of active and reactive power flows, that is the motto. That is the motto, the target. Now rotor acts, forget about that. No flicker. This flicker, that I have not discussed here also. Flicker is, say, supposing we have a grid, right? Now when you connect some source, what is going to happen? Different source. It cannot so happen with any control that 100% seamless. There will be some difference in phase, there will be some difference in voltage, etc. So that can cause, if the connected source is a very high capacity, let us say hundreds of megawatts, so initial flicker will come. So that also has to be reduced because this wind system, they are frequently connected and disconnected because of the non-predictability of the wind or variation, wide variation of wind. Okay. So if it so happens, then there is grid will be unstable. And then this is the negative side. Cost is a little bit higher because we require a high-end power electronics, right? So this is the. Now let us come to this the first part of our technology what we are trying to discuss. That is the wind turbine. Okay. Now wind turbine, as we see, it can be of many types. It can be of many types. Now basic category by this axis of the turbine. Now some turbines, the axis is horizontal here, and for some turbines the axis can be vertical. So the turbines are categorized by, firstly, their axis, horizontal axis turbine, vertical axis turbine. Now mostly the power generation is for vertical axis. Horizontal axis turbines, they are not designed for high power operation. They are designed for mainly domestic purpose, or you can say with a rating of less than 5 kilowatt usually. Big turbines are not economical or not very feasible also, based on the wind dynamics and all those things. Now we will discuss this for horizontal turbine, okay, horizontal axis turbine. Now the blades, you see, these are the blades, right? And this is called nacelle, and within which we have the motor also, and the connection can be within this this pipe or in this frame, within this frame, installation frame. Depending on the, you can say, the operating wind speed range, because in some places average wind velocity will be very high. Say, suppose you are trying to install in Andaman. So naturally, there you see possibility of a lot of say storms and all are very high, right? Or if you install here, let us say, average wind speed is very low. So depending on which you have to select that what type of, how many blades. The blades can differ from single blade to say multiple blade system. 2, 3, multiple, 6, 8, like that. And those designs are beyond our discussion because mostly mechanical part, and just for your knowledge I am telling you that selection of this is a factor. Right? Let us say we have selected. So now these blades, they can rotate on their own axis. Okay. Now keeping this axis as say vertical plane, this angle of rotation from the vertical plane is known as pitch angle, right? If it rotates small with respect to horizontal axis, the pitch angle is small. This means this. Now wind is flowing like this, so when pitch angle is increasing, naturally we are bypassing more wind. When it is like this, it is actually hitting total, means our conversion is high, right? For high wind speed, we will try to rotate it along the direction of the wind. Okay. So this is what. Now this is known as pitch angle. Now this blades have some length, or you can say when they rotate, there is a radius of rotation, right? The radius of rotation is actually the length, approximately you can say, approximately the length of the blades. Right? Now there is a term called as tip speed ratio. Tip speed. Now tip speed means actually when it rotates, now the linear velocity at the tip of the blades. That is actually, if the rotational speed is omega, as it is shown here, so tip speed will be omega r. R is the radius, so linear velocity is omega r. Now ratio means you have to take the ratio against the wind speed, right? That means omega r by v1. This is known as tip speed ratio lambda. And v1 is the wind speed, and its unit will be in meter per second. Right? So now this turbine has a, I am not deriving the equation. The turbine has some characteristics for different with the conversion of energy with respect to tip speed ratio. Right? So in the x-axis, tip speed ratio is increasing. On the y-axis, there is a conversion factor, or it is known as coefficient of power, right? Cp. It is in percentage. Now for C, these are the blade angles, different blade angles, 1 degree, 3 degree, 5 degree, like that. As we see here, 1 degree means almost horizontal, so conversion is more. That means for same lambda, we are getting more power. Right? So this is the highly nonlinear characteristics for the conversion, and it is limited by Bayes limit. So that is not the point of discussion. Anyway, that you will get to know. So this is the characteristics for Cp with lambda, right? So now power is actually what then? Cp is a coefficient of power or conversion factor, if you see. So input power into this conversion factor will give you the power converted by this turbine. So then this is actually half P input power that can be calculated as half rho AT V1 cube from this formula of kinetic energy and all, taking a cylinder and everything. So this rho is actually the density of wind. AT is the swept area, pi r square, and this is B1 cube. And then Cp is this one. Cp is this one, lambda theta is a function of lambda and theta. Okay? Cp is the function of lambda and theta. So then this becomes the power equation, right? Now from here, what we get, this P is highly dependent with wind speed. It is proportional to, keeping everything constant, it is proportional to V1 cube. So if your speed changes by 10%, 1.1 power 3 overall power change, right? So therefore, the power availability also can be very highly fluctuating, apart from other things, right? So this is the thing what we know, and then there is some in PV system. I think many of you work. You are acquainted with the term MPPT, maximum power point tracking system. Na? In wind also, the same thing can be applicable, but with a little bit difficulty. Why difficulty? Because it is more dynamic. Solar, very slow changing, right? From the morning, unless and until there is a huge cloud coming over say over half an hour or so, otherwise there is a very slow change. So the controller get ample time to operate at that point or find that operating point. Now here, finding operating point is a little bit difficult because of the fastness of the changing speed. Now similarly, converting that into that generator torque and generator torque speed for different wind, we get similar characteristics. So for different wind speeds for the turbine, say for horizontal axis turbine, we get generator speed versus generator torque, right? Now we get similar characteristics and we get some point, some generator speed for particular wind speed where we see that the torque is maximum, available torque. That means if my wind speed is 12, let us say, and if my generator speed corresponds to this, then I get this torque. Otherwise, for the same wind speed, if I operate generator here, I get lower torque. Clear? Idea is clear. So we have to find the suitable speed, rotational speed for the turbine generator set, so that it operates at maximum torque or maximum power position. Right? So then our aim will be to operate this generator at those speeds where it has maximum torque situation. Torque can exceed the rated torque. If you try to operate always at that torque, right? So wind speed can increase in such a way that your operating torque can be higher than the rated torque, which is not also expected or not allowable, you can say. Simply because if the torque is higher, the torsional stress on the shaft will be above the rated value. So naturally, at some point, there can be deformation, etc. Or there's some crack, anything can happen. So then, actually, aim would be that as soon as it reaches maximum, rather rated torque, as soon as it reaches rated torque, so we have to keep this torque at constant value. By some control, maybe with some pitch angle, maybe with motor side control, generator side control, flux, etc. We can have flux equation for the machine, which is variable with a function of, say, injected power, injected reactive power or so. So we have to find some way out so that we operate in this trajectory. This is the trajectory of operation for maximum power. That's why I said
this is a mechanical torque developed.
Mechanical torque.
The electronic torque can be controlled by some generator part
Uh-huh.
by changing some.
Right. But stable operating point where your mechanical torque and electrical torque are same. Then what you do? You have to bypass some power
Yes.
through that pitch angle control.
Why pitch angle control will control mechanical torque.
Mechanical torque, and then also that electrical torque also you can have the same way by weakening the plaques or etc. So both things has to be coordinated. Okay. So this is that is why I said that this is actually a little bit more difficult from the solar MPPT system. Why it didn't have this type of limits? Okay. So there we have installed the capacity is up to the maximum limit, and we have always lower value. But here it can reach even higher value. You cannot install your wind power based on the maximum availability. Otherwise, it will be a problem. For low power, it will be a loss of efficiency problem. So then, in this trajectory we can operate. Now we are finding few things. Like say here, this point A you see, from here, point A. This point A is known as cutting speed. Cutting speed means where it starts generation. You cannot generate from zero speed, right? From zero speed you cannot generate. You have to generate at some minimum speed. Because the system has some losses, you know. System has some losses. So whatever your wind power is giving, now that power you have to extract minus losses, right? So therefore, actually, from zero wind speed or just at starting, you cannot generate. So the starting speed nowadays for these turbines are around 3.5 meter per second. I am giving you meter per second wind speed, horizontal speed. Now below which we cannot generate. We have to either stop or we have to do something else. Now this is one research area that I had started my talk like to find out some areas. So aim is now towards generation from lower cutting speeds, maybe 2.5, maybe 2 meter per second, like that, so that the system can get connected. Now, as just few minutes back I told you, sometimes it is disconnected, sometimes it is connected. If it is so, then there will be flicker problem, because seamless transfer is just a theory. Now, when you come to practice, it will never be seamless. So then, if we can reduce it, it can get connected at even lower speeds, so that our system becomes more reliable. Okay, if speed increases, okay, slowly it is providing power. So then, this is one research area, and we have taken also one project from Ministry of New and Renewable Research, MNRE, Ministry of New and Renewable Energy, right? Energy system. So our target is to bring it around say 2 to 2.5. So let us see how it is possible or not possible. But this is an area of work. Next comes this one, where we operate at MPPT very easily. Now this has become speed limit means this one. Around this one, this is not the speed limit, actually I don't know why it is written. This one actually is the speed limit. Now this speed limit is actually to restrict it from reaching torque above rated value. Now after that, we can have some more say point of operations at higher wind speeds, till it reaches at such a speed that it is limited. It is under limit. That means even if we bypass almost say 80-85%, that also giving torque which is maximum more than the rated value. So we have to stop it, right? So that is known as shutdown speed. So our operating area will be BCVE. and here there will be another point 8, right? So it has taken from a literature, so I have not distorted it. So that is this is the, I mean, operating range should be from this to this, generator speed range, this to this, right? So this is the card. Now this has been explained by this one also, that as I have said that below cutting speed it is clocked, it is known as parking mode. It is parked, nothing. Then up to this it is generator control. When it reaches say, 1 per unit power. After that there is a pitch control. Pitch control along with generator control, right? Generator plugs and etc. And after that it is a shutdown. After that it is a shutdown. So this is what actually has been just explained in these few slides. Parking mode, generator control mode, pitch control mode. And then this one. So same thing has been described here. Right? So any, I think will be question our section after this lecture. That will be better. Now we are talking about these horizontal axis turbines. Now the thing I explained has been also given in the slide. So these horizontal axis turbines, they are very large turbines usually. They can be designed up to nowadays we don't have a turbine more than 10 megawatt single unit. So 8 to 10 megawatt is normally the highest limit till date. Okay. And here say the common are 2 megawatt, 3 megawatt per unit, 1 unit, right? Now these are actually mounted where wind velocities are high power operation. And these are reflected here. Wind velocities are high, right? Now we have said here, this is hub, rotor blades, and the nacelle generator, etc. This is a common thing, right? Now we see the horizontal axis, sorry, vertical axis. Now in horizontal axis, we see that the motor is, rather the generator is mounted here. The cabling is to the tower and then it comes, right? Now when you see the vertical axis turbines, they are mainly of low power applications. Even at rooftop also, nowadays GE, General Electric company, they have floated one project to operate this at low wind speeds, say 1 meter per second, 2 meter per second, like that. For small scale, 250 watt, 500 watt, for rooftop operation, and wind and solar can be combined on the rooftop, and so that all the residential systems, residential areas become self-sufficient. They don't take electricity from outside, because these two are complementary. Wind and PV, they are actually complementary. In majority, the record whatever we have found in majority of the places, like say solar is available in the daytime and wind is mostly available in the evening and in the dawn, in the night, like that. And we can reduce the storage. So if we combine both of them, because what we do in normal home power system, you see there is a battery. So in the daytime it can store energy, and in the battery they can supply. But battery is again a hindrance, as well as it increases the cost, maintenance, everything, and then waste management also. That battery technology is not so developed till date. So the energy density factor, we are all dependent mostly by lead acid cells, which is mostly available. And dumping those, recycling those products are also difficult, right? So that is the reason they are planning for a model system to combine this wind, small scale wind and PV system. And then here you see the generator is at the base. Generator has the base, and we have a bevel gear so that the motion is converted horizontally, vertical motion to horizontal motion. and then and it is having the advantage to convert wind from all the directions. This horizontal axis also, and so that there is a rotation on this axis, so it can align. So this statement is not very true that it can only convert from all directions. Is not true. Here also we can have that arrangement. Like many of you have seen some arrow-like thing behind this turbines, behind this nacelle, and then it rotates. It rotates along the direction of the wind, and then conversion can be done. So this is same thing also can be done here also. And then here construction on buildings to avoid ground level turbines. Building, rooftop construction can be easily done. So this is a structure. So this is only the symbolic structure. That you don't see that all turbines will look like this. So there are various, you can say various variants of this picture. Okay, depending on the manufacturer and speed, power, etc. Now I will give you some interesting idea regarding the technology. As I have said, that we have said that about 10 megawatt wind turbine, particular single unit, right? Now we have also showed that this is the radius, the length of the blade is the radius, just approximate. Forget about the diameter of this motor, okay, a generator. Now diameter of this area will be actually 2 into R, right? Now come to this one. Now say this is a design now, but say for a 225 kilowatt turbine, let us say 225 kilowatt turbine, the diameter, you see, is 27 meter. Just to see how huge it can be, and as it is proportional to area, that means it will be proportional to d square, right? That means 2 times the diameter change means 4 times the power change. So if you go for a 2.5 megawatt, the diameter is 80 meter. Just to imagine, a 80 meter turbine is rotating, right? But giving only 2.5 megawatt. Thermal plant is what? Is giving 210 megawatt per unit very easily. 500 megawatt units are very easily available. Now, 140 meter dia nowadays it is available, giving around 8 megawatt to 10 megawatt. I forgot the figure, I'll tell you. 140 meter dia. A turbine of 140 meter dia is rotating. So they are not mounted in locality because of the sounds and of course availability of wind, as I have said. That power has to be available. So they are mounted in coastal areas like this. I have seen in Baltic states, they are Sweden and all, they are on the coasts, they are mounted at tandem. They are connected, and their cabling is through the sea and it is coming to the grid. Okay. So then, if you have 10 megawatt units, so 10 such units will give you 100 megawatt. So like that, there is a combination. Okay. So this is the case. Offshore installations. This is known as offshore installations, and some are onshore installations. Okay. Onshore installations are smaller because the wind consistency is not that high. Inconsistent wind is there. So this is what. Now we will again prove, rather corroborate our statements. What we have said from before, that why we could not control the wind and what makes us to control the wind. Then we come to the electrical technology, right? That how we do that. So some system idea you should have. Otherwise, just mere discussion about some few generators and all will not make sense. So see, I have talked about that area, that year, 1980, if you remember, 1980, to 2040. Sorry, to 2020. Right? So 1980, you see, this is the, typical availability of wind turbine, another evolution of wind power system. Now the blue shade denotes the controllable power, or electronically controllable power. The white shade denotes the uncontrollable power, right? Now 1980s, what I have said, that we just started to manufacture the power BJTs, power MOSFETs, and thyristors are available, and some processors are started coming. Now you see, our technology was such that we could have maximum turbine of dia 15 meter and generating 50 kilowatt power. And controllable power is a dot at the same time, almost small. So this has got some significance. Say, if a 50 kilowatt motor, rather generator, is generating, now total 50 kilowatt we cannot control, we control only say 1 kilowatt. So that is shown in this shaded area. Rest 40 of that turbine. That means wide range, and then rest power is uncontrollable. Right? Now 85, same dot. 20 meter increased and 100 kilowatt, right? 1990, 40 meter, again further increased, 500 kilowatt. That portion is still remaining same almost. 1995 onwards, the Texas Instrument processor, I don't know how many of you are acquainted with that TMS 320 series that came. Because I started working from that point, so that is why I remember. So then controllable part is slowly increasing, you see. As the controllable part is increasing, the dia is also increasing. 2080 meter, 2 megawatt. 2005, all controllable, 124 meter. Now power devices are still not very stable. Okay. Now power device. Now 2005 onwards, I think you people remember that. তার ঠিক আছে একটু ব্রেক করে নাও, তবে এইটা তাহলে এক্সপ্লেন করে দিই, এটা তাহলে বলে দিই, তারপরে 2005 onwards, if you remember, microchip controllers, that microchip, you know, PIC series, PIC series controllers. Any one of you is acquainted with some microcontroller programming, microprocessor, Texas Instruments, SGS 1000, ST Microelectronics, or you can say this microchip. From 2005 onwards, they came into picture. Okay, so then we had everything controllable. And 2011, 2018 estimated means that was actually just 18. Now it is like that. You say 190 meter, 10 megawatt. That's what I am telling. Entirely controllable. And in this area, পরে চা খাবো, আমি তো চা খাইও না, আমি জল খেলেই আমার হবে, চাটা লাগবে না, আমি চা একবারে সব So actually, 2018 onwards, we have, if you remember, Raspberry Pi. You have that, you know. So this is very common. So this controller technology has become very common. So entire power is controllable, and we have reached almost a limit. And now technology is starting towards others also, that we will discuss a little bit. So now we have a single unit of around 10 megawatt, which is available with a huge dia of turbine, 190 meter dia turbine. You cannot imagine that, 190 meter dia. Unless and until you see it from the front, it's there. After I think traversing through the basics, or you can say overall system, we will come to the actual thing, like say how we generate this wind power with the help of this generator technically. technically. Now we have seen a lot of evolutions, lot of other things. But now the discussion point is that how it can be actually generated. Now, just we started discussing that variable speed generation is our target. So we cannot have a system which runs at fixed speed. We will lose lot of wind power for that. Now, power electronic converter is I think, is an inevitable device that we require. Now, the machine part, or you can say that generator part, there can be 4 types of generators. Can be now, there are these first 3, or rather you can say first 2 were the mostly used generators from the olden times. Nowadays, these 2, out of which this is mostly popular. Now, first one is synchronous generator, as we see. Second one is squirrel cage induction generator. So we have ruled out DC generator, as we have said, that we are not going to use DC generator because of those problems. And third one is with the help of sleep ring time machine. Now that will be called as W-fed induction generator. WECS means wind energy conversion system. This wind, WECS, that is what, WECS. With synchronous generator, squirrel cage, with sleep ring. The other name, the most popular name is W-fed, and this one is 100% new. WCS with brushless W-fed motors, and these are the research, you can say, the research areas or research topic nowadays. These and these 2. Okay. Now, synchronous generator. As we know, everybody knows that how it can generate power. Like say thermal plant, what we do? We couple a turbine and that rotates at fixed speed. So there it is very easy to rotate at fixed speed because we have the controllable power. We can control the speed governor system, so that our speed is constant. But here we don't have. Rest mode is same. So if you do not have that system, so naturally your generated voltage will be variable voltage and variable frequency, because E is proportional to both speed and F is also proportional to speed. So to avoid that problem, what we have, so this AC power of variable power frequency and variable voltage nature is rectified. And then it is filtered. Then it becomes a smooth DC voltage. And then it is inverted with the help of fixed frequency converter. Fixed frequency inverter. 50 Hz. So that frequency shift problem is gone. Now voltage problem also can go if we have an inverter which is boost in nature. Boost inverter is also available these days. Otherwise, we should have some intermediate DC link, say DC to DC buck boost converter, so that it can regulate the output voltage to a fixed value. Right? And then the field supply for this synchronous for this alternator can be adjusted with the help of this rectifier, right? So then this system is easy. Variable frequency, variable voltage, just convert to DC. Now DC voltage, there is no frequency, only magnitude can vary. Now that magnitude also you can fix through a DC to DC converter, or you can have a boost inverter, right? That can fix the voltage here, that voltage. But there are problems. Problems is, first of all, you need these 2 converters, right? 1, 2 at least. And that must be of same rating as that of this alternator. If the alternator is 2 megawatt, you have to have 2 megawatt this, 2 megawatt this. Right? Then the problem is nothing. it will increase the cost and reliability because you are having more semiconductor devices with high power rating in between, right? And then designing inverter of say few megawatts is not a very easy job. There are not a single device. There should be some devices that will be operating in parallel. Now parallel operation, if you those who have practical sense, you will see no two devices are similar. They are coming from same dice, but their characteristics will never match semiconductor. So a lot of say mismatching during with current sharing, heating, etc. So therefore, it is not very reliable supply, not a very reliable solution, you can say, reliable solution. And at the same time, you see here that DC excitation is also a problem. Although in the scheme we have given the same voltage, generated voltage for the excitation, and it will start generation from the residual magnetism part. But it may so happen that it always runs at lower speed, so the voltage will be less. Now the field power also will be less. So if field is less, so again generated voltage will not be at that value because it is proportional to flux, right? So all these things have made the scientists or the engineers to think in a different way. In the next version, they did this. Instead of that, they had permanent magnet synchronous generator. Now, as we see that the alternator ratings required are not that much because for an alternator, 2 megawatt, 4 megawatt are tiny. Because see, alternators of 500 megawatt, 700 megawatt is very common. So 2 megawatt is nothing. So permanent magnet design is not a problem. It can be designed very easily. And then we have this DC-DC boost converter, grid side converter, diode side rectifier. So everything is same. But the thing is that when you give a permanent magnet, now your field excitation become uncontrolled, right? Now when the speed is high, the voltage level at this also becomes higher. You are getting me? In the above case, we could have controlled this rectifier to for a lower current or higher voltages. You can control, no problem. But here, since the field is fixed, so ordinary, and we are having an ordinary diode rectifier, so there is no control over the voltage generated. But so now actually this technique has also been altered. So instead of this simple diode rectifier, we can have active front end rectifier. I think you have heard of active front end, where it is actually the same like this grid side converter. Now it has got, instead of diodes, it has got this IGBTs, and that can regulate the active and reactive power from this system. Now reactive power can be so adjusted that if the voltage is high, it will act opposite to the field. That means net field is reduced, like say armature reaction effect of inductive loading. But so that helps to regulate the voltage. Right? So then again, things are possible, but we need again 3 converters, 1, 2, 3, along with a transformer if required, of same rating as that of the PMSD. So the problem is with the cost, space, and reliability. But anyway, we can do it. Yeah. Until and unless we have a better system, we have no other option, right? So earlier days we used to generate like this. Now after that, now this is the picture of this rectifier chopper. This is the rectifier, and then this is the boost converter, this is the grid side converter. So this is the detailed picture. This is the rectifier, this is the boost chopper, or you can say boost converter, along with this the IGBT, this diode, capacitor, and this inductor. And then this is the grid end converter. Okay. Now, it can achieve so many things, like say maximum power point we can achieve, and you can have a control of grid side converter to control the DC peak voltage and unity power factor. Again, one thing you should also know that the role of this converter, how to control. Main thing is we are designing many things, but we should have the role, we should define the role, right? Now, say the role of this is to dump the variable frequency AC power to this as a grid, to DC, variable voltage DC. Now, this role of this is to boost the DC voltage to a certain value, right? Now, the role of this.
So how variable voltage can be fixed voltage? Actually, speed of the generator will be always varying. The voltage fluctuation will be there. And
So this is here
after
variable voltage.
after
This is variable voltage.
After activation, variable DC voltage.
Now this boost converter, you can have a duty ratio control. Now you see what is the formula of boost? V output equal to V in by 1 minus D. Now if V in is varying, you can vary. That is why we have
to get constant DC.
Right. Now even if the DC is constant, actually this converter, if it does not face that power, where the power does not provide that power to grid, where this power will go? That means again the DC bus will swell. Now this converter will dump this DC power to this grid system. Now one statement we have given here, that unity power factor, right? Now this converter will be controlled in such a way that the power factor at this point is unity. Now what will be the advantage? If it is not unity, what is the problem? At unity power factor, the power is given by voltage into current, right? And at any other power factor is VI cos phi. So for same power, if your power factor is low, I will increase. For same power factor low means I will increase. Now I increase means more current stress on this device. It has to carry more current. Now when it carries more current, possibility of that there can be failure. So we will try for minimum possible current to be flown by this through this converters or the devices. So that is why we will require unity power factor also. Right? Neither, even not leading also. Leading also it can supply VAR, but current stress on this device will be more. Okay. So for these grid systems where we are connecting these inverters, the reactive power source should be better to be other one, except these converters.
That means here transformer is not required.
Transformers will not be required.
Due to boost of
Why maybe, may not be. Because these statements are also, you see, it can so happen, it generates at a very low voltage. Now the boost converter has got some limit to boost. Say if you boost it above 3 times the value, there will be instability in the converter. You know, you can there are analysis, etc. So that also will lead to some problem, right? Therefore, in that case, it is better to have a transformer here. Okay, it depends on the application and up to which range we apply. But normally we are presenting some typical schemes.
So is it possible to maintain the power factor unity at that?
Yes, it is possible. It is possible through power electronic control. It is possible. Now, synchronous generator, almost these are the 2 schemes that are normally available. Okay. Now we come to the case of induction generator. Now, induction generator, as we all know, when induction motor operates as generator?
Above synchronous speed.
Above synchronous speed, right? Now, come here. Above synchronous speed, right? Now, synchronous speed will be defined by what? Defined by?
120.
That means where the F is defined by what? From some supply. So this thing is only valid when we have a grid connected induction generator. Grid connected, right? When you connect to the grid, then only the frequency is defined, because that flux, rotating flux speed is defined by this grid frequency, 120 F by P, and you rotate this prime mover above synchronous speed and it will generate. That's all. Now this scheme is very simple and has some beauty also, because with small variations of speed, there is no shift in frequency. Right? There is no shift in frequency. Frequency is fixed. Right? And it has been already connected to the grid. So seamless, nothing.
So frequency fixed.
Frequency fixed, because grid frequency is fixed.
Grid frequency.
It's always grid frequency. Right? And you see power flow, active power is here, reactive power is from the grid to the machine, if there is a load, and it will also take from the grid.
So if the grid frequency is fixed, then in place of three-phase induction generator, we can use the three-phase synchronous.
Synchronous generator, the operating mode is different. Synchronous generator is what? DC supply at the field. So you have to have a prime mover that generates. Here, the operating principle is different.
The field is not required actually. I don't know.
Here it's a rotating field. No. Here you have to apply force to go above synchronous speed. So that work done by the force is converted to electricity. There you have a magnet which is rotating in a coil, and that's how you are generating. Okay. So that is why these two modes are entirely different. Got it? So now this Q is coming from this grid to the machine as well as to the load, and P from the machine, if it is load is more, some P will be also supplied by this grid. If P is less, then whatever it takes, rest P will be going to grid. But again, there is a problem. This thing is very simple and we used to do it earlier also. There is a problem. What is the problem? Now we were discussing regarding this, operation above synchronous speed. Now I am giving you an example. Say we have a 4-pole machine and a 50 Hz grid, right? And the machine is such that its operating sleep is 4%, right? 4% of, that means what is the synchronous speed for 4-pole? 1500 RPM. 4% of 1500 is 60 RPM. That means we have a rated torque here at speed 60 RPM above synchronous speed. 1560 RPM. Right? So just we have discussed from the beginning that we cannot go above rated torque. So our upper limit is fixed. 1560. Right? And then lower limit at 1500 torque is 0. That means no generation. That means around 1% at least above which we have some generation. So 1% of 1500 is 15 RPM. That means 1500, 15 to 1560. This is the operating range. Almost fixed speed operation. So it can generate only at fixed speed.
1500
with a very small variation. 15 RPM to 1550 to 1560. 45 RPM variation. That is nothing for the wind. Right? So it's a fixed speed operation. So if it goes below, it tries to operate as a motor. So instead of generating, it will consume power from the grid. And if it goes above, so motor is at danger. It is operating at higher torque. So then, this is a major limitation. This is a fixed speed operation. Now, what is the variable speed operation? Variable speed operation is this. When we do not connect to the grid, it is known as self-excited induction generator, ACIG. And this is with cage type machines. We are all discussing with cage type machines. Now, self-excited means, excited means actually the flux. Now there, in the grid connected system, we were taking flux or rather absorbing reactive power from the grid. Here, there is no grid, it is directly load. So who will provide? So we have to provide some reactive power source, that's the capacitors. Right? Either in star or in delta. And when there is a speed variation, there will be generation. I'm sorry actually, there is one plot here showing the variation of the OCC curve. There is no board also which I can. Huh? I can use this board, huh? That will be helpful. Just come. So here, the frequency of operation, you see, frequency of operation is as per the speed. Now, speed is, because there is no fixed frequency there inserted. Whatever be the operating speed, accordingly the frequency of operation is there. That means, if you see here, this is your OCC for the generator. OCC is actually IM and this is PS, source voltage. Now if you assume the induction generator to be just like this, forget about all leakage path, right? So this OCC is varying with speed. For higher speed it will be like this, for lower speed it will be like this, right? And then in the equivalent circuit, you see I have connected a capacitor. This is what? This is the stator side. This is the load, you can say, load, and this is the XM, this is the XC, capacitor, right? So now, what is going to happen? Now, this part is due to the residual magnetism, right? Supposing we are rotating at some low speed, let us say. Now, at that speed, maybe a little bit lower, some small voltage is generated at the stator, right? Now, as I have a capacitor, there will be some current through this, capacitive current. Now, if you have a phasor, say inductive current is this side, capacitive current is this side. Just reading the voltage. This is the VS, whatever, I have a VS here, stator voltage, right? That means the current which is flowing through the capacitor is actually neutralizing the magnetizing current required. That means as if it is supplying the flux. So what will happen? Now there will be, and at that speed, let us say, I have a capacitor line. This is known as capacitor line. Like
Resistance line.
In a DC shunt generator,
Resistance line.
that due to the capacitive current, more voltage is generated. This side is voltage. Now, for that voltage, more capacitive current. For that, more capacitive current, more voltage. Like that, it goes and it settles there, where these two plots coincide. Right. Now, at this, I have some voltage generated. Now, if my speed is higher, so naturally, this frequency of operation will be, actually this XC is actually 1 by omega C. Now if speed is high, omega is higher, so it will be more stiffer, so it will come here, capacitor line, and we can have more voltage generation. Right? So that's how it can generate, and at the same time we have a variable frequency generation. Variable frequency, but it is generating and at wide speed range. But this power is not usable. This technology we knew 100 years back, say 1888, what we sold, even turbine was there. So this is nothing, I mean people have that brain that it can be easily done with the help of a capacitor, but this power is not usable. Why? Because of the variable frequency nature. Where will you put? In fan, it will rotate at different speed. Refrigerator, it will rotate. Load means actually mainly motor loads, but we have. It can be only useful where we have some loads which operates with RMS value, say heating load. heat up. Nothing. Any frequency, DC, AC, it will heat. Right? So those loads will only be applicable. Some heating, something, etc. Even some lighting loads also these days, I mean lighting loads can be operating at any frequency because these are all rectified units. In electronic controllers, we have rectifiers at the front end, so then there is no problem. That time that was also not there. Okay, 1888 we are talking about. So we knew this thing but could not operate it over a wide speed range. Only grid connected operation, fixed speed operation was possible. And controllable power is of very small value, that's what we have said. Now, these are all the derivations from this equivalent circuit and all. Now, with the advent of the power electronic technology, we could convert something similar to what we have seen for the synchronous machine. How? Now, we have connected here the same system, one active front-end converter at the generator side and another converter at the grid side. And this transformer is optional, maybe or may not be necessary depending on the DC bus voltage variation. Forget about this transformer. Concentrate on both this. Now with this, see, it's a variable speed operation. Now, what is the role of this front-end converter? That means here. Now, its role is to provide a frequency or rather reactive power to the system at that frequency where it is generating. That means, interestingly, if you see, that was our original plot, right? That was our original plot at rated frequency. Now at lower frequency, what will be happening? Like this. Right? Now we need to operate at this speed for this frequency, for generator, at this speed for this frequency, for this generator, at this speed for this frequency. Getting me or not? If you do not understand, no point in discussing.
Okay.
Huh? So then, since we have a converter here, we can easily operate it always above synchronous speed as a generator. Not getting. See, for this I have said, I am giving an example. The 1500 RPM is the synchronous speed. Now our limit I am saying 1560 RPM. Now say for this it is 1000 RPM here. Right? 1000 RPM. So for this speed could be how much? It says 1000.
4%.
Same 4% of 1040 RPM. Now when it operates at 1040, we can provide a power supply frequency corresponding to 1000. If it is say 500, say 520. That means 520 RPM, if it rotates, I will provide a frequency corresponding to 500 RPM. Always it is at generating position. Torque is negative. But variable speed. Again, the problem is with this, here DC is coming but at a variable voltage. Because the flux is varying, flux is remaining constant but speed is varying. So our voltage level is reducing. Like say, you have heard of VVF control, VVF control. So VVF means what? Frequency and voltage are varying in such a way that flux remains constant, ratio. Frequency decreasing means voltage is decreasing. Here also, frequency is decreasing, voltage also, generated voltage also will decrease. But we can have a transformer here or a DC-DC converter here that can easily boost it. And we can have total electronic control for this induction machine over the wide speed range. Right? Again, the problem is nothing but the converter cost. If it is a 2 megawatt system, again 2 megawatt, all these things like synchronous machine. But we are able to convert it. That is more important. Okay? With the help of power electronic converters. Now therefore, ability to make best use of available power, because wide speed range we are operating. Whatever power is available, we are trying to extract. Okay. Disadvantage, cost of power converter is high. Okay. And sometimes it eliminates the need for capacitor bed, but we can provide also here. Nowadays there are various schemes, you can read some research papers also. And we have also done some work. I don't know how much time I will get. I intended to show some of our own work in this type of systems that has been done. But anyway, so this is okay. This is first of all, we should cover up the theory, then more advanced things. So these are the general pictures. I think I can have half an hour time. Right? So this is all about, I will not discuss much, this is all about this squirrel cage system. Now when we say that this part, synchronous squirrel cage. So almost these two, they are all primitive systems. Only induction motor last scheme what we have discussed, like this variable frequency operation, is the result of the last 2 decades maybe, because with the advent of the, otherwise they are very old. Now this thing with doubly fed induction generator. I don't know whether it is, those slides are here or not, I missed it. No, it is there. Okay, we can discuss. Okay. Now initially we had starters for cage machines to reduce the starting current, but that reduced torque. Okay, if you remember. Dual starter, it was high current in rush, and then we had all the start delta and all the current is reducing, but torque is also reducing. But here, lower current and better torque. Right? How do we do it? By inserting resistance in the rotor circuit. Now, effectively what it does, it tries to shift the characteristics. Now, in my characteristics here, it will shift the characteristics like this. Now, in generator also, it will shift the characteristics like this. So, maximum remaining same, it will be coming here, but actually it will flatten. Curves are flattened with resistance. So here we have shown the this generator part only. That with resistance, this is with R external equal to 0. When R external is increasing, so we are getting these characteristics. Now, what is the result of it? Suppose we have a torque 1 per unit, right? Negative torque is generating. Now that 1 per unit torque used to appear at 4% slip. Just now we have discussed 4% slip, 60 RPM. Now same 1 per unit torque with higher resistance can happen at higher slip. That is what is happening. 10%, 12% slip. Now when the slip is 10%, so what is the speed?
Yes.
More.
Oh, sorry.
In generator side.
Generator.
That means 10% of 1500 is 150. So it is going up to 150 for same torque. For same torque, we can go to a higher speed range, 1650 RPM. Instead of 1560, we are able to go to 1650 RPM. Clear, na? That means we are getting wider speed range. Wider speed range at same torque. Right? So that was the initial motto, to generate through squirrel cage machine with rotor resistance control. Means at higher speed we will increase the rotor resistance so that my generation remains intact at that speed. Torque limit is maintained. Getting? So then how it was done? It was done with the help of this kind of circuit. Now this is what the resistive circuit, and then it's a chopper type of thing. Now when this is on, the resistance is sorted, you see, through the wires. because rotor has got AC slip voltage, slip S into ES. Rotor voltage is S into ES. And that 3-phase voltage is shorted. When it is off, resistance is in the circuit. So we can regulate this duty ratio of this chopping circuit or of this converter, of this transistor or this IGBT here, IGBT, to vary the resistance according to the speed, right? But again, our speed range is not increasing too much. It is only up to 1650 RPM or so, and at the same time, at higher slips, you see, the rotor frequency is high, and the rotor loss, rotor is with the resistance, so rotor loss will increase too much. So whatever benefit we are going to gain has been eaten away by the loss of efficiency. Okay. So then, unless and until we had some other things, we used to do it, but it was not a very efficient method. Okay.
Power recovery scheme, rotor power recovery scheme. You can add this here to get the rotor power to the grid.
Rotor power to the grid, that is the scheme that I will tell you. Now after that, this scheme came. That what you are telling, it is actually a rotor power to the grid. You cannot directly feed because it has got a different frequency, slip frequency.
Yes, sir.
So that another frequency converter is required. The same thing has been achieved by this scheme. Now here you see the stator is connected to the grid directly, and rotor actually is connected again to the grid with the help of two back-to-back converters. And this type of system is known as doubly fed induction generator. Why doubly fed? Because this can feed to both ways, feed to grid. One is this, another is this line. So we will just discuss a little bit more detail now. Now what is the advantage of this scheme? Now we can, actually this converter is effectively increasing the resistance, no doubt. And it is actually bringing back the power. I think you have heard the term Servius system or Kramer drive system in case of motors. They are handling powers. Now advantage is that these converters or this rotor power, whatever we have, is a slip power. You know, rotor actually handles slip power. Right? Slip power recovery system here. The rotor is slip power. That means these converters that will be operating at slip power. So slip power is actually S times
PG.
the PG. So PG, if you neglect losses in the stator, so PG is the stator power. So if your slip is 10%, the converter power will be 10%. Right? If the slip is 30%, so by this method we can go up to 30%. Will come. Now, if it is 30%, the converter power is 30%. So now see, the beauty is actually that we are able to control entire power by controlling this power only. Okay, so wind is providing power and we are trying to control the rotor power so that entire power is controlled. Now this scheme actually came in the year 2002 or so. 98 or 97 there was one paper in IET Generation, Transmission and Distribution, I think, I remember. And after that from 2002 onwards, actually this scheme became most popular scheme. Wherever you go, this scheme you will find. And it has overtaken all the existing schemes. Now, if you go to that slide where we showed that this one, that this, see here from 2005, all things are blue. That is because of that reason. Entire power we are controlling, 10 megawatt power, and we are 300 kilowatt. Sorry, 30% is 3 megawatt. So we are controlling 10 megawatt power by controlling only 3 megawatt power. So that is from this point onwards, we are able to control everything. 100% of the power is controlled. Okay. Now another beauty of the scheme I will discuss. So this is one thing, okay, slip power and all. And the role of this converter actually again is similar. It will provide reactive power to the system at the frequency corresponding to the operating slip frequency and bring the active power or provide active power to the system at that frequency only. Now when it brings the active power, it brings to the DC bus, and when it provides the active power to the machine from the DC bus, right? And this machine, this converter, this will again operate at unity power factor, and its role is to keep this DC bus voltage constant. How? Supposing this machine needs, this induction generator needs power, so when this converter fetches power from this grid, the DC bus voltage will fall. Now to make the bus voltage constant, it will bring power from the grid. On the other end, if it extracts power, the voltage will swell here, increase here, and then it will send power to the grid, dump power to the grid. So that's how it operates. And motto is for unity power factor, always. Okay. Now another thing, let us see. Let us see the equivalent circuit of this induction motor, the double fed induction motor or slip ring type. Now we have stator side and rotor side both accessible, right? This is the stator voltage, this is the rotor voltage. Now rotor voltage is at rotor frame, rotor reference frame, right? Now from the stator, if you see, you get actually V2 by S, because it is slip power, na? S, ES, and from the stator it is ES. So if you see from the stator, it is SES by S. Now actually from the stator you see VS by S. Now we have a rotor current which is an I2 at an angle theta, stator current I1 at an angle delta, and this rotor voltage is at any angle phi, let us say, and stator voltage is the reference voltage, right? So now you see the air gap power. Now if we try to compute air gap power crossing this air gap, so what will be is, this is actually the rotor power, total rotor power. Now rotor circuit you see R2 by S into 1 minus S. If you add them up, it will be R2 by S. So the power at this rotor is I2 square R2 by S, right? You concentrate here. And for 3 it is 3 phase, 3 I2 square R2 by S, this power, air gap power, plus, what is the power? The power provided by this converter, this is actually V2 into I2 into cosine of angle between V2 and I2. This is the power which is fed. This is actually then V2, I2, V2 by S actually, that is crossing. Okay. So now again, if you go for the power flow diagram, the mechanical power expression is well known. This is 1 minus S into PG, 1 minus S into the air gap power, right? And then you can have PM plus SPAG is PAG. PM plus SPAG is PAG. Now what is SPAG from this equation? SPAG is actually 3I2 square R2, which is actually rotor copper loss, plus 3 V2 I2 cos phi minus theta. Rotor side power, right? So now putting this, combining this, you can have PAG equal to PM plus SPAG. So SPAG is this. So this is the famous universal equation for this air gap power. So now see another thing. Say supposing we expect the generator to operate as generator, the machine to operate below synchronous speed. Below synchronous speed. So till now we have heard that when it is connected to grid, So below synchronous speed it is not possible because torque is negative, below synchronous speed torque is positive. So it will operate as motor. And let us say here we expect it to operate as generator. So then what will happen? In that case your air gap power will be negative because for motor air gap power goes from stator to rotor. Now when it is from rotor to stator it is generator. Now PAG is negative. This is our expectation that it operates. And my slip subsynchronous, that means between 0 to 1, positive. Positive. Now when the speed is positive, let us say S into PAG. এখানে এই যে S into PAG is this much, na? S into PAG is this two. S into PAG. So S positive, PAG negative. So SPAG will be negative if it is a generator. Now then this part, say 3V2I2 cos phi minus theta plus theta, then this two has to be negative. SPAG negative means this first two term summation will be negative. Now first term can never be negative. It is a rotor copper loss. 3I2 square R2. But we can make this one negative. Right? When phi minus theta is more than 90 degree, what will happen?
Negative.
It will be negative. Right? So this part can be negative and more than I2 square R2. So entire thing will be negative, and so that my SPAG is negative and then my PAG is negative. Correct? So then this part is negative means actually rotor is absorbing electrical power. So at subsynchronous speed, if we supply electric power to the rotor at some particular phase angle adjustment, etc., then it can operate as a generator. Right? Clear? And when it is above synchronous speed, let us say super synchronous, S is negative. Yeah, S is always negative. Super synchronous. And generator means PAG. It is also negative. Generator. So SPAG will be positive. SPAG positive means what? This part positive. This is always positive. But this positive means actually rotor is providing electrical power to the grid. That means it can operate both under subsynchronous and supersynchronous mode as generator by adjusting rotor supply. And subsynchronous speed, rotor will absorb power and stator will provide power. So net power gain is stator power minus rotor power. And supersynchronous speed, rotor is also providing power, stator is also providing power. Net power is PS plus rotor power. Clear? That means it can operate at a speed of 30% above synchronous speed to 30% below synchronous speed. Why 30%? Because above which actually there are various constants, 30 to 35% till now. There are various constants, like by at high sleep, rotor frequency will be high, then rotor core loss will increase very much. And rotor core loss increase means rotor losses, heating, etc. Machine thermal limit will actually exceed. And also, for a say 1 megawatt machine, 30% from the rotor and 1 per unit from the stator, that means 1.3 per unit power we are extracting. That is also violating the total law. So actually 30%, 35% is the limit till now. We cannot operate above 30%, 35% sleep. Even 30% you see, what is the speed range? 1500 RPM, 30% is how much? 450. That means 1950 RPM at upper limit. And another 450 below means 1050. So 1050 RPM is lower limit. So your approximately 1000 RPM variation we can have. So these two are the major reasons why this scheme has taken away, overtaken all the advantages of other schemes. Means you see high power energy, high power wind installation is 99% this DFIG installation these days. Okay, even more than that, 99.9%. So this is what we have, and this is the power flow diagram. This is very common. Same thing we have shown here, and those and the phasor diagram also. This can be corroborated. That one power is positive, one power is negative for the subsynchronous, and both power is positive for the supersynchronous, like that. This operation and all. So I think I don't have much time. It is 4:30 almost, 4:25. So I thought of to show you other things, grid synchronization techniques, and but in a single lecture it is very difficult. And inverter control things, lot of things I like to show. And something I will just show you. And this is the latest technology what I am talking about. That brushless W-fed generator. Just one line I will tell you. That brushless, till for the slip ring machines, we have the disadvantage of brushes and slip rings. Isn't it? We are providing rotor supply through brushes and slip rings. Now brushes are not maintenance free. Although it is not a commutator, less maintenance, but still there will be maintenance. Now the research was on to remove these brushes. Now initially a group of researchers, they had the idea of operating two coupled alternators or two coupled induction motors, slip ring motors. So that say one stator, another rotor slip ring, and another stator, another rotor slip ring. These two slip rings are connected, just rotating at same speed. So this power exchange is through this rotor, right? And that is converted, that concept is converted into a single machine, where this machine is replaced by two windings in a stator, in the first machine stator, and rotor is having almost a single winding with a nested loop. Okay, the block diagram is simply like this, but there are a lot of hindrances, and the scope of research here, is very high. Means a lot of persons are working over it all over the world. We are also trying to develop a machine like this. This is the block diagram. So two stators at stator windings at different number of ports, P1, P2. And one winding is directly from the grid, like that machine, DFIG, and another one is actually through a frequency changer. And here frequency also will be different based on the rotor speed, right? Like that DFIG scheme. And then there are some derivations, classes, and all these things. I don't know. I don't know that. I cannot have that time. And this is the scheme what we saw. Instead of the slip ring, from the second machine, we have the back-to-back winding, and this is the frequency changing. The first winding is known as power winding, and the other winding is known as control winding, actually. So this is the latest scheme, and the other one is actually brushless BDFRM, brushless doubly excited reluctance machine. The variant of this, another variant, is a reluctance machine.
It is not induction.
Instead of normal rotor, we have a reluctance rotor.
It is not induction generator.
It is induction. This one is induction. This is BDFM, brushless W-fed machine. Other variant is BDFRM, brushless W-fed reluctance machine. Instead of rotor, there is a reluctance rotor, means pole like a reluctance machine, and there is no winding. Further higher efficiency. These two are, nowadays research are very heavily advancing on this.
Vector control applied.
Everything can be applied, but concept-wise, there are certain things that are to be widely accepted. Vector control has become, after 2005, it has become bread and butter of all the, you can say, schemes, whatever I have discussed here. It is only a field vector problem, nothing else. So I conclude here, and some of the skills, this is our what we have developed some things, and then when we said that the co-generation scheme, wind, solar, both, something was here. Means in a single generator, we can have, say, this is the RSC and GSC, na? See, we discussed about that wind, solar, you can say,